it is possible to see the potential for wind gusts also from the sounding. Here in this view macro, I have mean wind speed on the upper row and wind gust speed on the bottom row. And I'm comparing 3 different models. And if you look at this area, for example, you can see that mean wind speeds are around 10 meters per second according to every model that I have here available. But also in the same areas, the wind gust speed is over 20 meters per second. And if I look at the sounding from here, that can be seen on the right side, I can actually confirm that this is correct. So what I'm looking here is something that we call a well-mixed boundary layer. So if a convective boundary layer is topped by a stable layer, turbulent mixing can lead to the formation of well-mixed boundary layer. And here you can see that the lapse rates are dry adiabatic, and then we have the inversion layer here. If you look how the wind barbs are behaving, you can see that at the lowest level, the wind speeds are quite shallow. So if I hover my mouse, you can see that the value is around 10 meters per second, which is the same value that you can also see from this view macro. But then higher up, at the level of this stable layer, you can see that we have higher wind speeds up here. And if I hover my mouse here, you can see that it's around 25 meters per second. So this means that when the boundary layer is well mixed, these wind speeds higher up can actually propagate to the surface. So that's where the terminology comes from. So well mixed means that everything is kind of circulating here. So that's why even though your mean wind speed can be around 10 meters per second, you can have individual higher wind gusts of 25 meters per second in this point and using these values. We can check another point, maybe somewhere here, for example. Well, now you can see that the well-mixed boundary layer is very shallow and there is no significant probability for wind gusts in this area. Sure, you can see that the mean wind speed is between 5 and 10 meters per second and the wind gusts are around 10 meters per second more. But still, this place is not that favorable for these kind of wind gusts. So we can check at the surface level, wind speeds 10 meters per second, higher up here, wind speeds 18 meters per second. So once again, we have confirmed what we can see from the surface data, so from the raw data. If we want to have high wind gusts in convective situation, we need to have something that we call an inverted V shape in the sounding. So if you see this kind of shape where your temperature is rising towards the surface and dew point temperature is decreasing towards the surface, it kind of forms inverted V shape. And that's one feature that could lead up into a situation where you have higher wind gusts at the surface. We will come back to this when we are talking more about the convection, but it's just good to know that if you see this inverted V shape at the lowest level, you know that it's favorable for wind gusts. If the sun is hitting the ground very efficiently, like during the midsummer, you can also see a feature that is called over-adiabatic layer, in which your lapse rates are actually higher than dry adiabatic lapse rate. So here is an example of that, but it's very small, but you can still see it. So at the surface, the lapse rate of this forecasted sounding is actually sloping a little bit more than these dry adiabatic lapse rates. So these over adiabatic lapse rates are absolutely unstable conditions. So these air parcels can easily travel up higher in the atmosphere. One thing you can also easily see from the sounding is the total cloud cover or the coverage. And we are using it in percentages. So I'm going to give you a few examples how to say the total cloud cover in the percentage But you can also just as well use octas, for example. So when we are forecasting total cloud cover, we are paying attention to different layers of cloud. And we know that when our cloud base is below 2 kilometers, we are having low-level clouds, then we are having mid-level clouds, and higher in the atmosphere we are having high-level clouds. And you might know from the experience that you can actually see sun shining through the high-level clouds. So even though you have 100% coverage of clouds, but it's all high-level clouds, you can see the sun shining through. And if you are looking at the sky from the surface, you are not probably thinking that it's overcast, because you can still see the sun shining through this high-level cloud, and you might even feel the warmth of the sun rays on your skin. So that's why we need to consider this a little bit differently. And this is also the reason why you should consider sounding as your primary tool to figure out what the total cloud cover is, and hence not trusting blindly to the model and its presentation, because model thinks it differently. Here we can see that we have only low-level clouds. We don't have any clouds in the mid-levels or even in the higher levels. And this cloud cover here is around 500 meters thick, but since it's low-level clouds, it's probably going to be blocking most of the sunshine. So I would say that this is 80% total cloudiness. Let's take another example. So here, once again, we have low-level clouds, but the coverage is now higher. So I would say that this is completely overcast, so total cloud cover is 100%, because this is almost 1 kilometer deep. And when you have low-level clouds that is around 1 kilometer deep, you can say that it's completely overcast. So sun is not shining through at all. So here we have another example. You can see that we have, once again, we have low-level clouds here, but this is very shallow layer. It's not very thick layer. We also have something almost close to the boundary of mid-level clouds, and then the rest of this sounding is clear, so no clouds at all. Model thinks that the total cloud cover is 91%, but judging from the sounding, I wouldn't say so. So here, this is probably covering 40%, and this part a little higher up is probably covering less than 10%. So all in all, if I put this together, I would say that the total cloud cover is around 50%. So it's significantly less than the model is saying. And this is the reason why you need to do this forecasting on your own. You are doing it better than the model itself, because you have a different understanding of the total cloud cover. Let's take another example. Now we don't have any low-level clouds. The tropopause is very low at this time, so these are all high-level clouds. And since they are high-level clouds, the layer is very thin actually, so it's only like 2 kilometers. And when you have high-level cloud that is around 2 kilometers, maybe even 3 kilometers, you can expect sun shining through this layer. And I would say that in this kind of situation, total cloud cover is around 30%, not more than that. But the model, of course, is thinking that it's a little bit more. So it's saying almost 100%. Here is an example of a clear sounding, so no clouds at all. These two lines, so temperature and the dew point temperature, are not touching at all. So clear skies. Here I have high-level clouds, and the thickness is around 2 kilometers, so once again 30%. But I know that this is a frontal system that I can see here, so this precipitation is from a front. And since my sounding is from here, I can try to take a sounding a little bit closer to this precipitation area, and let's see what happens. So you can quite easily see that the cloud layer is actually getting thicker and thicker. And the closer I'm approaching this precipitation area, the thicker the cloud is going to be, starting from the higher up, coming towards the surface. So this is a textbook example of warm front. So here in this point, I would say that the total cloud cover is 50% because there is already quite a lot of these high-level clouds. And once again, if you just look at the model, total cloud cover is somewhere between 70 and 100%. If I once again approach a little bit more this precipitation area, you can see how it's getting thicker and thicker and thicker. And now we are already in 4 kilometers. And this is something that I consider to be 80% of mid-level clouds. And the reason I'm changing it to be now mid-level clouds and not just high-level clouds is that when I'm looking from the surface to the sky, I would choose a weather symbol describing the total cloud cover according to the cloud layer that is closest to me. So since there are no low-level clouds, the closest cloud layer to me is mid-level clouds. That's why when we were further away from this front, I could use the symbol for high-level clouds because that's the closest one to me. But now that we are closer to this front, I would use mid-level cloud symbol. And since the cloud is already 5 kilometers deep, I would say that it's enough to give me a feeling of total cloud cover being 80%, but not completely overcast. And then of course, when I'm more approaching the front, I have a rule of thumb that when my cloud is reaching from the top to around 3 kilometers, that would be a sign for me to put a symbol of overcast, but middle cloud overcast, not low-level clouds, because I wouldn't consider this yet to be low-level clouds. Here in this point, this cloud is almost 1 kilometer deep, so I would say that this is 100% low-level clouds. In this example, I have clouds in many layers. I have high-level clouds, this would be around 30%. I have a little bit of mid-level clouds here and also here, so alone it would be probably from 10 to 20%. But still, how I would choose my weather symbol would be according to the lowest cloud layer, which is here. And here, since the two lines are actually touching each other at the ground level, that would be an indicator of fog for me. So I would not use a weather symbol of completely overcast low-level clouds. I would use a symbol for fog. In this example, once again, I don't have any low-level clouds here, but I do have some mid-level clouds and higher-level clouds. So all in all, even though there is a little bit of high-level clouds and mid-level clouds, I would say that the total cloud cover would be around 30 to 40%. This layer is not very thick, and even though this cloud layer has a little bit more emphasis to the total cloud cover when comparing to the high-level clouds, overall, I would say that this sounding would be 40 to 50% mid-level cloud. And in this example, I have around 30% here the mid-level clouds, and then high-level clouds another 30%. All in all, it would be probably closer to 50 to 60% of total cloud cover. And this is something you have to learn yourself, how it works to work with the sounding data and how to interpret the data into a cloud symbol, for example. So it's quite empirical method, but it works just fine, actually. So try to do this, because your results might be significantly better when compared to a situation where you just blindly believe what the model says the total cloud cover would be. But not all clouds are seen with these two lines just touching each other. We also have convective clouds, and here is an example of that kind of situation. So if you look at the sounding, you can quite clearly see that there are no stratiform clouds. These lines are not touching each other at any point, so no stratiform clouds. But we still have clouds in this situation. and these clouds are convective clouds. Convective clouds always have a little bit of updraft inside of them, and when we have an updraft, we should have a profile, even the narrowest one, of K. So